Welcome to the video on the sampling distribution and the standard error of measurement. In the last chapter, we explored how if we have a normal distribution and know the mean and the standard deviation for that distribution, we can calculate a z-score and get the corresponding percentile for that z-score. This is all well and good if you know this information about the population. Unfortunately, in the behavioral sciences, we usually do not know the population mean or the population standard deviation, and we're left to guess what it's like based on what we know about the samples drawn from that population. The good news is, as we saw in the previous chapter, we know that due to sampling variability or sampling error, depending on what you want to call it, we can expect that there will be some variability in the sample statistics from one sample to another. This happens because each sample is likely composed of different people drawn from the population. Let's see an example of how this works. Let's say we have a population with a mean equal to 4. Due to sampling error, we know that samples drawn from that population can vary. So in our example here, we're going to draw 17 samples from this population, each one with the same sample size. So here are our samples. The first one has a sample mean of 7, then we have a sample mean of 6, and 5, and 4, 3, 5 again, and 3, and 4, 2, and 6, and 3, and 4, and 4, and 5, and 1, and 4, and finally 2. Believe it or not, the variability that we are seeing in these 17 samples is actually the good news. Clever statisticians a long time ago figured out that if you took a whole bunch of samples of the same size from the same population, that most of those sample means would be centered around the population mean, with fewer and fewer sample means the farther away you got from the population mean. Furthermore, if you were to construct a frequency distribution from thousands and thousands of these sample means, you'd be left with something approximating the normal distribution. Let's take a look at this data here from these 17 sample means and see what the distribution might look like. This distribution that you're seeing here is called a sampling distribution. As we can see in the graph, the mean of the sampling distribution is equal to our population mean of 4. In addition, we can also see the shape of the distribution looks pretty similar to that of a normal distribution. Of course, you are thinking, you made those numbers up, and you could have made the mean and the distribution look any way you wanted. True. However, according to the central limit theorem, when the sample size is relatively large, say greater than 30, and the mean of the sampling distribution is equal to the population mean, we can also calculate a standard deviation of the sampling distribution in much of the same way that we would calculate any standard deviation. However, we don't have to bother ourselves with doing it that way. Instead, we can estimate this number by taking the population standard deviation and dividing it by the square root of the sample size. Now, I know what you're thinking. What good is any of that going to do me, since you said that we are unlikely to ever know the population mean or the population standard deviation? And you'd be right. It doesn't seem very useful, except those same clever statisticians also figured out that we could make a reasonable estimate of the standard deviation of a sampling distribution by using sample standard deviation instead of population standard deviation. When we do so, we call it the standard error, or SE, and the formula becomes SE equals S, which is the sample standard deviation, divided by the square root of N, or sample size. Here's the really cool part. When we know this information about the standard error and the shape of the sampling distribution, then we can figure out the probability of getting a sample mean of a certain size with known population parameters such as the population mean and the population standard deviation. When we do not know these populations parameters, which will be most of the time in the behavioral sciences, we can use the standard error to get an idea of what the population mean is like given the sample statistics. This allows us to make inferences from samples to populations that they came from and make decisions about them with some degree of certainty, which is really pretty awesome when you think about it. But more on that in the chapters to come.